In this video, I'm going to demonstrate how to design a template to select an orifice plate. Now, this is going to be your lab 12. So the first thing I want to do is to look at my given parameters. 0.7 specific gravity. Now, we're going to be using this company's orifice meters. AFCO is in California. So we're going to be looking at their orifice meters. So we have to look at their specification and order for the right one that's going to work for this application. So I want to fix my flow rate to be 10 million standard cubic feet per day. So I need to find the right size of orifice plate that will work for this. Other things I need to know is, now this one, okay, I want to buy a plate that will not be larger than 20 inch in diameter. Then the upstream pressure is 800, upstream temperature is 80, downstream pressure is 350 psi. Now I want to choose an orifice plate line size 14. Now that's the company's, so we have to look at the company's catalog on what is line size 14. What do I need to know from there? So let's go to the catalog. This is the catalog. Line size 14. Okay, let me go to my line size 14. This is line size 14 there. If I look at line size 14, A is the size of the plate. Okay, let me show you the plate before I even continue. This company, they have two types of plate. One is the paddle type. The other one is the universal type. Now the difference is that the paddle type has drain, G, small drain, that will allow liquid to be drained out when the gas is flowing, if there's any condensed liquid. So I actually prefer that type of plate. So we're going to be using that plate. So now D is the internal diameter of the pipe that's the orifice meter is going to be connected to. Then A is the maximum size of the plate itself. Okay. Then D, small d, is the orifice, size of the orifice. So we need to know A, D, and small d. Then we're also going to determine the size of the vent. You have everything in the catalog. So now let's look at A. So what is my specification? I say I don't want it to be larger than 20 inch. So for line size 14, line size 14, my A that is close to 20 inch is 1938. So I'm going to order for A number 600. So they understand. If I say line size 14, A600. Then what is D? I continue there. D, this is D. D is 13.25 inches. So that's the inside diameter of the pipe. So I'm going to use that in my template. So let's go straight to the template. I'm going to open the template. Now, this is the input I'm going to put in the template. I'm just going to do that first. Okay, so this is the template. So let's fill out the input first. My upstream pressure is 800. Temperature 80. Downstream 350. D, that's what we're going to find. Inside diameter is 13.25. Gas specific gravity is 0.7. So that's my input. The rest I need to find. Okay. Now let's find Z first. We have to get used to using Breedbex. And in the remaining part of the course, we're going to be needing Z. So get used to know how to use the Breedbex now. So I'm going to open Breedbex to find the Z. Now Breedbex. So, I already filled it. This is 800. This is 80. And this is 0.7. The rest is 0 because I don't know them. 0, 0, 0. So I'm going to look at now this is my Z. I copy that. I go back to my template. Let me put it. Okay. I paste value there. Value. Okay. So the next thing, okay, this one is, I'm going to be selecting the different tab. For orifice meter, we have 4 different types of tabs. Corner tab, flange tab, vena contractor, and pipe. Now the tabs means where I'm taking the pressure, upstream and downstream. So I'm going to be determining the distance of the tab from the orifice plate. For corner tab, the pressure upstream and downstream, they are taking right there at the plate. So let's look at, okay, you look at the table there, F to H. So I use 1 for corner, 2 for flange, 3 for vena contractor, and 4 for pipe. L1 for corner is 0. That's the upstream distance from plate. And for downstream is also 0 because we are taking the pressure at the orifice. For flange, upstream is 1 inch. Downstream is also 1 inch. Now for vena contractor and pipe depends on the diameter of the pipe. So let's look at the formula. For vena contractor, upstream distance is D and downstream is D over 2. So here I'm going to put equals D. I just click on D, 13.25. Then here, downstream equals D over 2. I click on D / 2. For pipe type, L1 is 2.5D and L2 is 8D. L1, I'm going to put equals 2.5 multiplied by *D. I click on D. Then I come here, equals 8D equals 8 multiplied by, I click on D. I enter. Okay. So I got my table for the tabs here filled. So the difference is just the distance from the plate where I'm taking the pressure. So now I've gotten all my input. Now this one, I'm just going to be changing this. So let's say I want to try corner tab. I put 1 there. My first calculation is going to be for corner tab. So let's fill in the calculated values. Upstream temperature, that's in Rankine. So we know what that is equals. The temperature, C11 plus 460. 460. Enter. Now the next one is L1. Okay. Now, Excel should be able to put in the value of L1 whenever I change the tab type. So how am I going to do that? I can use if, but if I use if, it's going to be a lot of ifs. If equal 1, if equals 2, if that's a lot. There's a short function in Excel which I don't need to do all those. It's called lookup. So I'm going to say equals lookup, L-U-L-L-L-O-O-K up, lookup. Okay, I'm going to open the bracket. Now the lookup, the first argument is, what am I going to look up? I'm going to check this. Whatever I put here in the tab, that's my lookup value. Okay, says lookup value, that's my lookup value. So I put comma. So where am I going to check for that value? I'm going to come here. It's going to check all these numbers here. Wherever it sees 1, that's my... I already named that cell. Just those numbers, I named them tabs. So it's going to write tabs. Don't worry about that. Then I put comma. So it's going to look for tabs. It's going to read whatever I put there. Then look in tabs. And it's going to enter what? L1. So the value is going to enter is L1. So I'm going to highlight all this. I already named that L1s. Okay. So I close my bracket. So what Excel does is, it checks this number, whatever I put here, then look for the tab, then look at the corresponding value for L1. So that's it. I'm going to do the same thing for L2. So it should be 0 there. Yeah. Because L1 is 0 for corner. This one also should be 0. So I'm going to do the same thing here. Actually, I can... Oh, what's all this? Okay, let me type it. Equals lookup. Oh no. Okay, so it's going to be C17. I'm going to look up C17. Where is it? C17. Okay. C17. I'm going to look at C17. Whatever I find in C17, you look in the tabs. Now this is L2. I also named these L2s. If you highlight them, it's going to give you L2s. So I just change that one to 2. Okay. L2s. Okay. Now diameter ratio. That's equals small d divided by, I'm going to put a number there so that it doesn't put 0, divided by big D, which is this inside diameter. So let me say I put 7. Let me put 7 inches there. I don't know. Okay. Now the orifice area, so equals pi, pi, open bracket, close bracket, that's pi, star, multiplied by d squared. That's the small d. I click on that. I do square. Shift 6, that's cap 6, 2. That's pi d squared divided by 4. Now, see, this d is given in inches, but we want to find the area in square foot. So I have to divide again by 144. So it's pi d squared /4 / 144. So that would be full squared now. Pi d squared at /4/144. Now density. This is my density. Now remember, this density is in pound per square foot. No, pound per cubic feet. But we have to express the density as slugs per cubic feet. What we're going to do is we type this formula and we multiply by the conversion factor. Here is 0.031. So that will convert the pound to slugs. So let's insert this formula first. Equals 2.7. Actually, I can just 2.7 multiply by, let me multiply by the conversion factor straight away. Multiply by the conversion factor, that's C18, multiplied by what? Pressure, 800, that's C10. Then what? Divided by Z. No, multiply by specific gravity. That is C15 divided by Z and divided by T. Divided by Z, C16, then divided by temperature and Rankine, C26. Okay, enter. So that's my density in slugs per cubic feet. We're almost done. The next one is the longest one there. Now you have to pay attention there, because we are entering this formula there. This formula, the entire formula there. So it's long, but if you just follow the way it's written, you won't make any mistakes. So let's do that. That's the discharge coefficient. Equals 0.5959, 0.5959 plus 0.0312 multiplied by star beta to the power 2.1. Beta is the diameter ratio, so I click on that. Now shift 6. Now will give me my cap 2.1 minus 0.184. I don't need the 0 because it's 0 point. It's a decimal. Then multiply by beta to power 8. I click on beta again. Shift 8. Shift 6. 8. Cap 8. Then plus 0.0029 multiply by star beta. I click on beta, cap 2.5 multiply again star. I open the bracket. I'm just following the equation. Then 1,000,000 slash the Reynolds number. I'm going to click on the Reynolds number here. That's 19. I close the bracket. Then raised to power 0.75. Shift 6 cap 0.75. Now plus 0.09 multiply by star. I open the bracket. L1 I'm going to click on L1. That's L1. Oh. Let me start again. Where is it? Oh, 0.0. Okay, let me continue. That's L1 C27 slash slash D. Let's see, 13.2. Okay, I close the bracket. Then cap. No cap, sorry. Multiply by. I open another bracket. Beta to power 4. I click on beta. Cap 4. Shift 6. 4 slash divided by. I open another bracket. 1 minus beta again to power 4. Cap 4. I close the bracket. Then I close the other bracket. See, it ends with 2 brackets there. Then minus 0.0337 multiply by, I open a bracket, L2, I'm going to click on L2 there, C28 slash D, okay, I close the bracket, then multiply by beta cube. I click on beta again, diameter ratio raised to power shift 6 3. That's it. If Excel doesn't make noise, it means all the brackets are properly closed. Good. So that's my discharge. That's the longest thing there. Now we need to find the flow rate. Now look at it. We want to find the flow rate in mega standard cubic feet per day. That's why you have, for those who of you who did this lab work earlier, I forgot to put the conversion factor there, because without this conversion factor, you are calculating it in cubic feet per second. So to convert to cubic feet per day, you need to multiply by this, because the pressure again needs to be in pound per square foot. Since you are given pounds per square inch, everything that's factored out, you need to multiply by 1036.8. If you need to know how I get 1036.8, just email me. Now, so I'm going to put the formula there, equals 1036.8 multiplied by CD. I click on that, C32, then multiply by area. I click on that, then multiply by square root SQRT. I open a bracket, then 2 multiply by, I open another bracket, P1, I go up, P1 minus P2, I close the bracket. Okay. Slash divided by density. I click on that. That's C31. Then divided again, slash. Now this one I have to put it in bracket. Bracket 1 minus beta to power 4. Beta is my diameter ratio. I click on that. Shift 4. I close the bracket. Then I close the square root bracket. Must end with 2 brackets. Good. I'm done. I just need to analyze what am I giving? I want to fix the flow rate. Okay, now for corner tap, for the diameter I choose, it's giving me 16 million, but I want it at 10 million. This is 16,423. That's 16 million. But we want it at 10 million. So I need to reduce the diameter of the orifice. Now, let's see. Now, again, the company, they supply the orifice in increment of 1/8 inches. So now look at it. If I say area, that means 8 inches plus 0. The last number is just the 1/8. I mean the eighth. So area is 8 inches plus 0/8. That's so it's 8 inches. Area 1 is 8 inches plus 1/8, which is 8.125. Area 2 is 8.25. What is 2/8 is 1/4. So and so on. So we're going to, for the 8 series is going to be 7. No, 8. 0, 1, 2, 3, up to 8, 7. 8, 7 should be 8 inches plus 7/8. So everything is like 0, 0.125, 0.25, 0.375, 0.5. So let's look at, okay, let me see, let me try 6. I want to get it down to 10. Oh, you see, so that's 11 million. So let me try 5. 5 is too small. What? I want it to 10 million. Okay, 5 is too small. Okay, so let's go. So it's between 5 and what? And 6. So let me try what? 5.5. 5.5 would be 50. Okay, I just gave you all these numbers as an example. Even the one I'm using is not in this table. So 5.5, I know that's going to be 50 what? 50, 54. Number 54. 5.5 is, again, it's too small. The next one is 5 point what? 5.625. Oh, that's too much. Okay, so that's too much. So I'm going to use, so 5 is the best thing. No, 5.5. So 5.5. Well, that's just, so I have, oh, what did I calculate before? 5.5 is 98. So I'm going to copy that. That's for corner tap. Place value. Paste value. So the orifice number there is what? That's 5 and a half. That's 54. That's number 54. Now let's try flange. Just make sure I get everything right. Yeah. Okay, so let's try flange. I change this to 2. L1 should be 1 1 there. 1 1. Okay. 98 22. The same thing? No. Almost the same thing. I know if I put 5.625, it's going to be 2. So I think it's going to be this one. Okay, the same number 54 will work for that. So number 54. Let's try the next one. Vena contractor. I put 3 there. That should be 9847. So that's also 54. If I try 55, I know it's going to be 55. It's also going to be too much. So I don't need to really waste my time on that. Now let's try the last one, 4. So let's still keep the same diameter, 5.5. 96, this one is low. Let's try 5.625. 5.625. Wow! It's just over by 70. Okay. So it's also 5.5, 54. I'll go back to 5.5.